Okay, let's look at some applications of the Mobius function. We'll just do a couple examples. First, we're going to sum all of the integers relatively prime to a given number n. And then we'll look at the characteristic function of square-free numbers and estimate how many square-free numbers are there up to a given value x. So let's recall the characteristic sum property of the Mobius function. If we sum over the divisors of n of mu of d, this will equal 0 for all integers except for 1, where it equals 1. Now, I want to use this as a characteristic function for a different set. So let's see, how can we use this to identify when a given integer k is relatively prime to n? So think of n as being fixed, and I want to identify when a given integer k is relatively prime to n. So what we do is look at the following sum. Suppose I sum over the divisors of the greatest common divisor of k and n, of mu of d. Well, this sum will equal 1 when the number we're summing over, which is the GCD, is equal to 1, and it'll equal 0 when that GCD is greater than 1. So this sum is identifying precisely those values of k that are relatively prime to n. And then you note the condition d dividing the GCD of k and n is equivalent to saying that d is a divisor of k and d is a divisor of n. Now, one direction there is trivial. Certainly if d is a divisor of the greatest common divisor, then it must be a divisor of k and n. And then there's a theorem we proved earlier that said that any common divisor of two numbers is in fact a divisor of the greatest common divisor. So these are equivalent conditions right here. Okay, theorem. Let's sum all of the positive integers less than or equal to n that are relatively prime to n. And I claim that sum will equal n times phi of n divided by 2. So we can write it like this. Sigma, as k goes from 1 to n, subject to the constraint that k is relatively prime to n, of k is equal to n phi of n over 2. Proof. Okay, so I want to use the characteristic property we just were observing. So if I want to sum k going from 1 to n subject to this constraint, what I do is I turn it into a complete sum. Okay, but now I have to put in a characteristic function that would equal plus 1 if this condition here is satisfied, and would equal 0 if this condition is not satisfied. So what I place right here is the characteristic function we just observed. So you sum over the divisors of the GCD of k and n of mu of d. Right? This quantity right here is equal to 1 precisely when k is relatively prime to n, and it'll equal 0 other times. Then we do what mathematicians always like to do. We switch the order of summation. And before I do that, let's recall. So we have sigma k equals 1 to n, sigma d divides k, d divides n. So let's recall that this condition right here is equivalent to saying d is a divisor of both k and n. And then the terms we're summing up are k times mu of d. Okay, so if we're trying to evaluate a double sum, the instinct is to switch the order of summation. And then we have to ask, okay, what does D run through here? So K is an index, so it's changing, but N is fixed. So D ultimately is just running through divisors of N. And then we have this quantity mu of D that depends on D. And then K is going from 1 to N, but it has another constraint that D must be a divisor of K. And the term depends on K like this. Okay, so let's go ahead and write that down again. So we got equals sigma D divides N mu of D, K equals 1 to N D divides K of K. Now what type of sum is this inner quantity here? Well, that's just one of these sums. Well, no, let's put in one extra step. D dividing K. So let's say that K is D times L, where L equals 1, 2, 3, to what? Well, K can get as big as N, so that says L can get as big as N over D. So I'll put that step in. K is D times L. Okay, then the D here doesn't depend on the parameter L, so I can factor it out using the distributive property. So I'll put a D there. And then we're left with a sum as L goes from 1 to N over D of L. Okay, so what does that sum here look like? That's just 1 plus 2 plus 3 up to N over D. And we've all seen a formula for the sum of the first N numbers. So sigma 1 plus 2 plus 3 all the way up to N is just N times N plus 1 over 2. So in this case it's N over D times N over D plus 1 divided by 2. So let's write it like that. And then break that into two pieces. We'll have one piece which will have mu of D, D times N squared over D squared with a 1/2. And then there will be another piece that'll just have N over D times 1/2. Okay, and the first piece, we have a 1/2. N squared is a constant. I'll pull that out. And here we've got mu of D over D. Okay, that's a familiar looking quantity. And on the second piece, I've got a 1/2 with an N. The D's cancel out, and I'm just left with sigma D divides N of mu of D. And that's also a familiar looking quantity. So what do we get here? This quantity we did last time is phi of N over N, and this quantity for N bigger than 1 is what? 0. So assuming that N is bigger than 1, this whole thing just boils down to 1/2 N squared times phi of N over N, which is 1/2 N times phi of N. Now, what happens when N equals 1? go back to the theorem itself. So if n equals 1, then this is just 1 on the left side, and this is 1/2 on the right side. So it's a false statement. So I see that we have to put in for n greater than or equal to 2 here. Yeah. So for any n greater than or equal to 2, we have this statement holding. Okay, next, let's do another example. Let's find a characteristic function that will identify square-free integers. So I claim the following. Let's define capital F to be the sum over d going from 1 to n such that d squared is a divisor of n, of mu of d. So it's a little different constraint than we had before. Here I want d squared to be a divisor of n. Then I claim f of n is 1 or 0 depending on whether n is square-free or not. So if n is square-free, this equals 1. And it'll equal 0 if n is not square-free. So it's divisible by the square of some prime. So square-free again means it's a product of distinct primes. Now, to prove this, we'll recall a homework problem. So we showed that every integer can be uniquely expressed in the form a times b squared, where a is square-free. And as a consequence of that, you prove that d squared is a divisor of n if and only if d is a divisor of b. So when I prove this, we're going to just say this sum so I'm going to express n as ab squared. So it's the sum d equaling 1 to n such that d squared divides ab squared, and that would mean d divides b. Right? That's the equivalent to saying d squared is a divisor of n, that d is a divisor of b. Aha, now we're just down to the characteristic property we started with. You're summing over to all the divisors of b. Well, that's going to equal 1 or 0. It'll equal 1 if b equals 1. And it'll equal 0 if b is greater than 1. Well, what does that mean? To say that b equals 1 means that n is of the form a times 1, where a is square-free. So if n is square-free, and to say that b is greater than 1 means that n, in fact, is divisible by the square of some prime. So if p squared divides n for some p. QED. So we've got a function that picks out the square-free numbers. And so our next goal is then to count how many square-free integers are there. So you might make a prediction before I turn the page. Do you expect that most integers are square-free, or that most integers are divisible by the square of some prime? All right, let's see what we come up with for the number of square-free integers up to x. So I'll let capital N of x denote that number. And then I claim we have that capital N of x is equal to a constant c times x plus an error term which will denote e of x, where the constant c is given by the infinite sum as d goes from 1 to infinity of mu of d over d squared. this actually adds up to a finite number, 0.607927 roughly. And the error term, e of x, is bounded by 2 square root of x plus 1. So note the error term is of much smaller order of magnitude than the main term, which is roughly 60% of x. So we're saying that roughly 60.79% of all integers from 1 to x are square-free, not divisible by the square of any prime. Now, why does this series defining the constant c converge? Well, if we look at the absolute value of the terms inside, note that if you look at sigma d going from 1 to infinity of the absolute value of mu of d over d squared, well, mu of d in absolute value is 1 or 0. So this is less than or equal to the infinite series 1 over d squared. And that's a p series with p equaling 2, so this is a convergent series. In other words, the series for c converges absolutely, and therefore it converges without the absolute values. Now, some of you may recognize what this constant equals, and I'll say something about that after we do the proof. This is actually equal to 6 over pi squared. We're not going to prove it, but I'll kind of point you in the right direction for how you get that proof. So 6 over pi squared, it's a number a little bit less than 6/9, so it's exactly this value right here. All right, proof. So n of x is the number of square-free numbers less than or equal to x. So sigma n less than or equal to x of 1, with n being square-free. So now we turn this into a complete sum over all integers up to x, and then I put in the indicator function, or the characteristic function, of when a number is square-free. And so that's sigma d squared divides n of mu of d. That's the function we said that was 1 precisely when n was a square-free number. Okay, now let's rearrange the summation. So we have to talk about the range of values that d runs through here. So d squared is a divisor of n, meaning d squared is less than or equal to n, which is less than or equal to x. So d is always at most square root of x. So when we interchange the order of summation, d is going to run from 1 up to the square root of x. Then we'll have mu of d, and then the sum over n, well, n is less than or equal to x, and the constraint is that d squared divides n. And we're just adding up ones here. There is no dependence on n in the term. So what is this inner sum? We're simply counting how many integers there are from 1 to x that are divisible by d squared. Well, we know what that equals. That's just square bracket of x over d squared. The number of integers from 1 to x divisible by d squared. And square bracket x over d squared equals what? Well, it's almost equal to x over d squared, but it's a little bit less, so this we have to subtract off the fractional part, so you subtract off a little epsilon that'll depend on d, where this epsilon is some number strictly less than 1. Okay, let's break that into two pieces. In the first piece, we'll have x over d squared, and in the second piece, we'll have mu of d epsilon d. And then I go one step further. So let's put it, well, we can put it on the next slide probably. So let's just rewrite this. Mu of d x over d squared and the second term was minus d up to the square root of x of mu of d epsilon d. And then we're going to turn this into an infinite sum. So I'm going to let d go from 1 to infinity of mu of d x over d squared, and then subtract off those values with d bigger than the square root of x. Mu of d epsilon d. Okay, this is the main term, and notice that main term is equal to what? So this is our main term, and these are a couple error terms. So let's call this one E1 and this one E2. Okay, so let's look at the main term then. That main term, we can pull the x out because it has no dependence on d. And look what we have there. This is our infinite series that converges and what we define to be the constant c. So this is just the constant c times x. So what are we left to prove then? So we must show that these error terms add up to at most what the theorem was stating. So the theorem claims that this error piece right here is bounded above an absolute value by 2 times the square root of x plus 1. So we need to show that E1 plus E2 is less than or equal to 2 square root of x plus 1. So I'm just using the triangle inequality and saying that the total value of these two is less than or equal to E1 plus E2. And so it suffices to prove this fact right here. Okay, let's focus in on each one of these error terms, starting with E1. So this is the sum where d is bigger than the square root of x of mu of d, let's come back here, x over d squared. So again, you can pull the x out, and we see that in absolute value, using the triangle inequality, it's less than or equal to x sigma d greater than root x of 1 over d squared, because mu of d again is less than or equal to 1. Okay, now let's use the integral comparison for this quantity here. So I'm going to draw the function y equals 1 over t squared. Call this the t-axis, this is the y-axis. And let's say we have square root of x right here. And then this would be the square bracket root x, and this is the first integer after that, bracket x plus 1. So this would be where the d values in that sum start. So you're going to draw this little rectangle right here, and then you'll have another rectangle and another one. Okay, so this sum, 1 over this first integer squared plus 1 over this squared plus 1 over this squared is going to be less than or equal to x times what? So if I take the integral from root x to infinity, I would still have this little piece right here. And that little piece is at most 1 over x, because this is the curve 1 over t squared, so the height at this point is y equals 1 over x. So this little rectangle here is of area less than 1 over x, and then the rest of this is bounded by the integral from root x to infinity of 1 over t squared dt. So I'm just comparing the sum of all of these pieces here with the area below the curve. And you have this little extra piece to account for. So we have x, 1 over x, and then this is t to the negative 1, going from root x to infinity. So that's x times 1 over x, and then we'd have 0 minus the evaluation at this one. Oh, and I forgot there's a negative sign coming into play here, a minus. So this is 1 over root x, and we just get 1 plus square root of x. So that's the bound on the first term, E1. And then for the second error term, we've got E2 is right here. Well, that's even easier to bound. So we've got d less than or equal to square root of x, mu of d, epsilon d. So bring the absolute value inside, use the triangle inequality. The absolute value of mu is bounded by 1. And these epsilon d's, those are also bounded by 1. Those are the little fractional parts. So this is just bounded by 1, and so we're just summing up how many positive integers are there up to the square root of x, and that's certainly less than or equal to the square root of x. Thus, we have completed the proof. So the sum of the two error terms in absolute value is bounded by 1 plus 2 times the square root of x. QED. But I want to say a little bit more about that constant c. So let's look at it from a probabilistic point of view. I'm going to let capital P denote the probability that an integer chosen at random from 1 to x is square free. That is not divisible by the square of any prime. So how would I calculate this probability? Okay, so for any prime p, let's let f of p denote the probability that an integer chosen at random from 1 to x is not divisible by p squared. So in order to be square free, I want it not to be divisible by 2 squared, and not divisible by 3 squared, and not divisible by 5 squared, and so on. So I want to look at all of these different probabilities. Well, what is f of p equal to? So 1 out of every p squared integers is divisible by p squared. So the probability that an integer is not divisible by p squared is 1 minus 1 over p squared. So f of p is 1 minus 1 over p squared. And so if I assume these events are independent, which they are not exactly, but we're just making a heuristic argument here, the total probability then is the product of the probabilities over all primes p. So here p is running through the different primes. So I want it not divisible by 2 squared, not divisible by 3 squared, and so on. So I take the product over all primes of 1 minus 1 over p squared, which just equals this infinite series with the Mobius function in the numerator. And this is the definition of C. Okay, I should say something about where does this equality here come from. Well, let's look at that product. So 1 over 2 squared times 1 minus 1 over 3 squared, 1 minus 1 over 5 squared, like this. And now imagine multiplying it out. You're going to have some terms that just have a single prime factor. So you'll have a 1, and then minus 1 over 2 squared, minus 1 over 3 squared, like this. Then you're going to run into terms that have a product of 2 primes, and those will have a plus sign. So plus 1 over 2 squared 3 squared, plus 1 over 2 squared 5 squared, plus 1 over 3 squared 5 squared, and so on. Then you're going to get products of 3 primes, and those will come with a negative sign. So 1 over 2 squared times 3 squared times 5 squared. And look what's going on here is that you're getting the square of every positive integer in the denominators exactly once, and the numerator is having this alternating sign depending on how many prime factors are in that denominator. And so that numerator is precisely mu of the value n that is being squared. So it's giving you the number. It's -1 to the number of prime factors in that denominator. As far as calculating that value of c, so we observed on the previous slide that c, which is this infinite series right here, equals this product over the primes. Now if I look at the reciprocal of c, c inverse, that would be the product over all primes of 1 minus 1 over p squared to the -1 power. Now think of this as one of these quantities, 1 minus r to the -1 power, or 1 over 1 minus r. And you'll recognize that that is just the formula for the infinite geometric series. 1 plus r squared plus r cubed, dot, 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 dot. And so this reciprocal quantity can be rewritten as 1 plus 1 over p squared plus 1 over p to the 4th plus 1 over p to the 6th, and so on. And now imagine multiplying out that product on the right-hand side. So you'll have all the 2's, 2 to the 4th, 2 to the 6th, like that. And then you'll have all the 3's, 3 squared, 3 to the 4th, and then the 5's, etc. When you multiply it out, you'll have 1 times 1 times 1 times 1 all the way down the road, You'll have some terms where you just take a 1 over a p squared together with a 1 times a 1 times a 1 times a 1. So you'll have a 1 over 2 squared. You'll get a 1 over 3 squared right there. I can get a 1 over 4 squared. Where's that coming from? 4 squared is 2 to the 4th. You get a 1 over 5 squared. Where's 1 over 6 squared coming from? 1 over 2 squared times 1 over 3 squared. So again, by uniqueness of factorization, this is sigma 1 over n squared. And when you study Fourier analysis, you prove that this series is exactly pi squared over 6, and therefore the reciprocal quantity, which is your capital C, equals 6 over pi squared.